We, the Indian Society of Heating, Refrigerating and Air Conditioning Engineers, ISHRAE, stand tall in the Indian industry with over 10,000 professionals as members and almost an equal number of student members. Founded in 1981 and headquartered in Delhi, we operate from chapters and sub-chapters spread all over India, bringing our entire industry together. Individuals become members of our society according to their professional and academic standings. Our roadmap of the future looks very bright, with thousands of new members joining this technical society every year and bringing in a fresh outlook to our industry intelligence. ISHRAE disseminates knowledge through its technical committees, which consists of some of the best minds of our industry. It publishes technical books, newsletters, and a prestigious journal, distributing the wealth of knowledge to all its members. Working with government departments, ISHRAE helps formalize industry codes and standards. ISHRAE promotes research by offering financial support to student members to carry out groundbreaking work in technology, systems and processes. Our educational wing, ISHRAE Institute of Excellence, organizes training programs and workshops to help members enhance their skill sets. Our specially designed certification programs under ICP, that is, ISHRAE Certified Professional, empower professionals to always be in step with the prevailing technology. Specially designed courses for technicians are offered to meet the ever-increasing demand for a skilled workforce. ISHRAE organizes exhibitions, conferences, panel discussions and product presentations throughout the country. We organize the industry's largest international exposition in South Asia, ISHRAE India, to showcase the cutting-edge technology, innovation and provide a platform for closer interactions amongst the decision makers in the industry. The ISHRAE exhibition is now growing from HVAC&R show into BFA, Build Fair Alliance. This brings together several allied shows connected with the building services industry all at one location. Our chapters organize several other popular events like ISHRAEConf in Delhi, Raycon in Kolkata, Symposia in Mumbai, TechFest in Goa, and many more. We are committed to provide training and career guidance to our student members through seminars, lectures, quiz contests and site visits. A-Quest, a prestigious quiz competition organized by ISHRAE to catalyze the transformation of the budding engineering professionals. ISHRAE provides a platform to potential employers to select student members for careers in HVAC and our industry at the ISHRAE Job Junction. Young minds are made aware of the need for saving power, clean air and sustainability. The K-12 initiative of ISHRAE focuses attention on school students' development to inculcate a scientific fervor and help develop them into responsible citizens. Speedy information is imperative to keep moving forward in this hyper-connected digital age. Searcher, a specifically designed search engine, is now available, which allows access to a well-catalogued database on HVACR and building services industry with just a few clicks. ISHRAE cooperates with various national and international bodies, industry, governments, academia, think tanks to promote the concept of sustainability, environmental protection and energy efficiency and conservation, to enter and explore the universe of the Indian HVACR industry. Log on to ISHRAE.in that unfolds a panorama of information Let us engineer a sustainable future together through ISHRAE.
Yeah. Hi, Sukta ma'am. Please share about our speaker, Ms. Shreya Kulkarni.
Thank you so much, Purnima. A very good evening, everyone. On behalf of Delhi chapter of ISHRAE, I welcome you all to this wonderful program on CFD for built environment by our speaker, Ms. Shreya Kulkarni, on this very special occasion of Earth Day. I'll take the opportunity to introduce Ms. Shreya. She's a proprietor at Floaten Solution with 10 years of vast experience in CFD for built environment. She completed her MSc in Advanced Computational Methods for Fluid Dynamics, Aeronautics, and Fluid Structure Interaction from Imperial College of London, UK. Being an engineer, and she's an engineer in aerospace engineering with PPI from University of Sheffield, UK. We welcome you, ma'am, on this panel program, and over to you, ma'am. Please take forward this session.
Thank you, madam, and thank you, ISHRAE, for inviting me for this session. Thank you to all the participants for taking time out and attending this session. I'll just share my screen now. Madam, it shows host disabled participant screen sharing. Can you enable sharing, please?
Purnima, can you please look into the matter? Just give her the host rights.
Okay, ma'am, just hold on. Yeah.
You're the host now, ma'am. Please take over.
Yes. Are you able to view my screen? I'll just put it on full screen mode. Are you able to view it?
Yes, ma'am.
Perfect. Hi, good afternoon, everyone. My name is ISHRAE Kulkarni, and I will be speaking about computational fluid dynamics for built environment. Just to understand what is fluid dynamics, fluid is anything that can be deformed under external stress. So it can be a liquid, any kind of liquid, from water to air to blood to any sort of fluid can be studied, oil. But in our case, considering we are talking about built environment and air movement, we look into air as our fluid for the fluid under consideration. And dynamics is anything which is in motion. So anything which is continuously moving, continuously deforming. So we are looking at air which is moving in and around our built environment. And we are looking at computational fluid dynamics to optimize a solution for the same. Now, when we talk about computational fluid dynamics, it means that we are looking at a virtual solution to our problem. In a real life, it is very difficult to understand how fluid motion is going to affect your environment, how it's going to move around within your space. So we use computational fluid dynamics to study the same problem in a virtual environment. What that means is we set up a problem, we look at over a period of time, we look at air movement within that environment in a virtual condition. So initially, when computational fluid dynamics was started, we needed rows and rows of servers with multiple server racks to do a very small problem with a very high computing power. So if you look at the bottom image, for some reason my cursor is not working, so I'll just speak through it. If you look at the bottom image, you can see that there are rows and rows of servers being kept and used to run a small problem. But now you can run the same problem on a desktop with a high computing power, but it can be done for a very complex problem. So now with the rise in computing power, you can evaluate much more complex problems right on your desktop. So what we look at is computational fluid dynamics, what it is all about, how the process is undertaken, and what kind of solutions you can get out of it to optimize your problem. So initially, before computational fluid dynamics was used to understand fluid motion, for instance, air or smoke within our system, what used to be done was hot smoke testing. What would be done is once the building is complete, usually a canister of hot smoke would be brought in, and it would then be opened, and the people involved would study where the smoke is moving within the building, whether there is any kind of smoke accumulation happening at some part of the building, and how much time it takes for that smoke to evacuate from that building. So there were two problems with this case. One was that the testing could only be possible after completion of the building. So if they had to bring in the smoke and do a physical testing, it would be post-completion. And the second would be that if there were any kind of problems identified during this testing, then whatever changes was proposed would be a expensive structural change. So it would not be an easy change to conduct after the testing was complete. So what computational fluid dynamics does is that it gives you a environment where you can simulate the same fluid flow. You can simulate how your air is going to move around in the system without having to have a physical prototype. So you can do it while the system is still on the design stage, while it's still on paper, and you can simulate the same in a 3D model to see how this flow is going to move around in the system and whether it's optimally designed. So in this case, you can see for a dentist chamber with the air conditioner on one side and the air purifier on the other side, whether the aerosols being ejected into the system is being taken care of by the air purifier or not. So things like that can be studied by computational fluid dynamics in a virtual environment. Now, how that helps with our problem is that you can test a design correctness right at the design stage. You do not need to physically prototype your building. So you do not need a structure to be in place before you can test whether your design is going to work or not. So this reduces physical prototyping. Also, because there is no physical prototyping, if there is any kind of problems that was identified at the design stage itself, it can be quickly redone on the design and re-evaluated right in that virtual environment before proceeding for physical prototyping. This reduces time investment, it minimizes failure, and it reduces costs. So just to take you briefly through the process of CFD, what you begin with is a 2D CAD model. Usually what you receive, 3D modeling is rarely done in India. So what you receive is a 2D CAD model, but you can convert it into a 2D CFD model and then a 3D CFD model in your CFD GUI. So you can have a CFD model as a base to begin with. The next part of the process is to apply boundary conditions. So what we mean by boundary conditions is, just going back to the previous image, this is a car park with 2 ramps coming down on the left side and multiple flashhead cutouts. The red in the center of the car park is the exhaust fans where it has been mounted, and then there are some fresh air fans mounted in yellow. And there are jet fans shown in blue around the car park. So now the next part of the problem, next part of the process is to apply boundary conditions. And what we mean by boundary conditions is the initial condition to the problem. So in this case, if there is any jet fans or exhaust fans being applied to the problem, that would be the boundary condition. For a thermal comfort study, if we are looking into air conditioning and we are applying a ODU or a indoor unit, that would become the boundary condition to the problem. Now, that would mean that we would need to have the physical structure, the physical equipment, as well as the CFM, the temperature through it, the velocity through it. So these data then become the boundary conditions for that problem. For a thermal comfort study, we also look into the heat load data. So heat being generated within the system. In that case, we have to look into the solar radiation through the windows, the walls, the ceiling, the heat generated by any equipment within the room, by the number of people within the room, and by lighting or electrical components within the room. So if you, I'm sure you're familiar with the heat load sheet, where you can calculate the amount of heat flux through each component, from walls, from people, from equipment, light, appliances, and the same then becomes the boundary condition for your problem, and you can apply it to your given conditions. The third kind of boundary condition could be a fire design. So in case of, if you're studying fire load and smoke movement, fire design then becomes the third kind of boundary condition you can apply to the system. What we mean by fire design is the fire load, that is the intensity of fire, the fire material. So what kind of material is on fire, that would dictate the amount of soot being created, the amount of peak heat, peak fire load being considered, and the fire growth curve, which is in 4 stages: the ignition, the growth, fully developed stage, and decay. This fire growth curve works as a function of time. It is approximated as a t-square time curve, fire curve, and the 4 stages are followed for any given item on fire. So to get these data, you can refer to some journals which give you a good idea of what kind of fire load you can expect for various items on fire. How much, at what time would they reach peak fire load? So that would be the growth curve for part of the fire, and at what time it will start decaying. So that you can get from these kind of data sheet. So if now we are looking at, say, chair 13, which has a material of wood frame, urethane foam, quilted cotton, polyolefin, or polyester batting with polyurethane reaction, and it has a maximum heat release rate of 874.2 kilowatt. The fire growth parameter and decay parameter has already been given in this particular sheet, the last 2 columns. And as per that, we can then calculate the t-square fire curve. So in this instance, when the fire starts at 0 seconds, it would attain a 1 megawatt fire load of at 200 seconds. It would attain a fire load of 874.2 kilowatt, which is the maximum heat release rate, at 187 seconds. It will have a flashover at 200 seconds, which means all the fuel has now been depleted and there will be a decay time. So from 200 to 500 seconds, the fire will now decay and it will completely end at 500 seconds. So this now dictates your fire design for this particular item. Similarly, if we look at a car on fire, we can have this same sort of fire curve where a maximum heat release rate of 4 kilowatt is considered, which is 4 megawatt. This is for a car with fuel. The fire material considered is flammable fuel, metal, plastic, carbon fiber, resin with polyurethane reaction. And in this case, the growth rate is considered as a fast growth rate of 0.188, and decay rate is considered as 0.064, which dictates that the peak fire load will be reached at 146 seconds, and it will start to decay at 950 seconds for a 20-minute fire. The 4th kind of boundary condition that can be applied to a problem is ambient conditions, which means your dry bulb temperature, your wind conditions, the humidity to be considered. So ISHRAE gives you the climatic condition for each station in India. It will give you the hottest month. In this case, for Bengaluru, it's April, with the peak annual DBT for n equals to 50 years as 38.4 degrees centigrade and wet bulb temperature as 29.6. In this case, the wind direction is 90 degrees. So north is considered 0, east is considered 90. South is considered as 180 and west is 270. So in this case, it's an east wind with a mean wind speed of 1.4 meters per second. So if you're looking at any kind of ambient conditions, external ambient conditions for your building design, you can refer to the ISHRAE climatic conditions, and you can get this data from it. And once you have applied all your boundary conditions for that particular problem, you would move to the next part of the process, which is meshing. So within that that space, that car park that we were looking at, we would then break it up into millions of cells. The boundary wall would be considered as the domain of the problem. And within that, we break it into cells in which for each cell, for each time iteration, we calculate a velocity, species transport like carbon monoxide. In case of fire, we would study the soot percentage, the visibility. So for that, we then resolve the domain into small cells. Now, why that is done is because for each cell, so for instance, if the domain is broken up into millions of cells like this, each cell has a face, a node, and an edge. And at the center of each cell, you have the computational node for that control volume, for which different parameters are calculated. And for each time iteration, so say for instance, t equals to n plus x seconds, you would calculate whatever parameter you're looking at, you would calculate that for the first cell. And then for the next adjoining cells, going forward to the complete domain. So for t equals to n plus x seconds, we would calculate velocity, temperature, visibility for every cell. And then we would restart that entire process for t equals to n plus x plus 1 seconds. There, the initial condition then becomes as t equals to n plus x seconds. So that's a time iterative method. It moves forward in time, and every calculation that is made then becomes the initial condition for the following iteration. And this continues until you get a stable condition, or if you're looking at a period, for instance, if you're looking at a CO simulation for a car park and you want to study 1 hour exposure, you would continue this process for 3600 seconds. So your iteration can be as small as say 0.04 seconds, and then it can go in an iterative manner from 0.04, 0.08, 0.12 all the way to 3600 seconds till the for that 1 hour exposure. So that is the basic process for CFD. Now, to calculate these parameters within that control volume for every kind of say velocity, temperature, pressure, fluid, species transport, how it's done is by a set of complex, I don't know what just happened. Yeah. Set of complex equations. So how it is done by solving mathematical equations for continuity, for mass, momentum, energy, and species transport. It is a science of predicting fluid flow, heat transfer, mass transfer, and chemical reactions. How it is done is by the finite volume method, the method I just explained. There are other methods like finite difference method, but that is used for structural analysis. For wind analysis, mostly finite volume method is utilized. The modeling is done by K epsilon turbulence modeling. It's a time variant transient analysis, and it uses large eddy simulation to resolve the fluid flow. And once we are done with the processing of the simulation, so we first spoke about pre-processing, where we did the meshing and the boundary conditions. Then we went through the process of running the simulation. And then the last part of the process is post-processing, where whatever data that you have received from the simulation, you then post-process to understand how your fluid is moving around in the space, and what kind of contours you can get out to understand whether it is working in the manner that you have expected it to. So in this case, for this particular basement car park, we can see that the fluid is moving from, the air is moving from all the fresh air points to the extract point in the center. And there is no stagnation zone or any underventilated zone. The velocity is above 0.2 meters per second all throughout the car park. We'll talk further about car parks when we go to examples. This was just to take you through the process of CFD. Now, when we talk about airflow, I like to say that there are 3 behavior of airflow that we should keep in mind while looking into computational fluid dynamics or any kind of design in general. The first is that air will always take the path of least resistance. What that means is, even if there is an open space from one end to the other, but if you have put a barrier of some sort even with 60% opening or 80% opening, and there is open space next to it, the air will always take the path of least resistance. It won't go through that 60% opening. It will go to the 100% opening. The second is that it will always take the shortest route. So for instance, in a system, if there is an exhaust fan and you have provided two fresh air cutouts, one is closer to the exhaust fan and one is further away, the air will always will be pulled in from the cutout which is closest to the exhaust fan. And third is hot air rises. So especially in thermal comfort studies, hot air always rises. Cool air will tend to descend. Now, just to take you through some case studies to understand how we can utilize computational fluid dynamics to optimize our problem and to understand airflow around the system. So starting with the basement car park, we look into airflow analysis first. So again, we start with a 2D CAD model, which has been converted to a 2D CFD model. In this case, the car park area is 21,500 square meter. There are 8 exhaust points in the car park. So the pink ones are the exhaust points. And then there are some fresh air cutouts in the car park. So all the center blue that you see is the fresh air cutouts. And then there are some blocked lobbies, staircases, lift lobbies, tank area, pump area, all of that has been blocked off. We assume that these parts of the car park has been blocked off by fire doors. This is the 3D model, 3D CFD model for the car park. So there are 16 cube axial fans, 8 in normal mode and 8 in fire mode, which are marked in red, and the 8 fresh air cutouts have been shown in blue. Now, just to look at fan placements, what we have is the top image showing velocity around the car park without jet fans, and the bottom image showing velocity around the car park with 24 jet fans. Now, why we want to do that without the jet fans is because we want to understand what is the natural airflow path around the car park. So from the fresh air cutout, how is the air moving to the exhaust? Once we know that, we can optimize the number of fans that we require, because we can identify what are the stagnation zones or the underventilated zones around the car park. Also, the other point being that we would want to maintain the natural airflow path and optimize that with the jet fans. So we do not want to move air against the natural airflow path, because that would be counterproductive. We want to maintain the natural airflow path and optimize the number of jet fans. So in this case, for the fans working in normal condition, without the jet fans, we can see that there are quite a few blue portions. Now, if I were to adjust the scale to 0.1 meters per second, what we consider as underventilated is when the velocity is less than 0.05 meters per second, and stagnant zone would be when the velocity is completely zero. So anything between green to blue would be considered as underventilated to stagnant zones. So without the jet fans, we can see that there are 50% underventilated zones and 25% stagnant zones in the car park. And we have optimized that with 24 jet fans to reduce the stagnant and underventilated areas. Now, looking at the velocity contours at the jet fan height, you can see that there are portions which are blue, which indicate underventilated stagnant zones. And considering the same, the jet fans have been placed in the car park to move the air in the flow of the natural fresh air path, and to optimize that, to basically get rid of all the blue and the green portions in the car park. So again, looking at the velocity scale at 0.1 meters per second, we can see that the jet fans have now reduced that underventilated stagnant zones in the car park. So basically, you can, if in case of any kind of optimization, any kind of further reshuffling of jet fans, you can study that with CFD. You can understand whether your system is acting optimally for that given design. Now going to the second type of basement car park analysis, which is CO analysis. Again, we are looking at a car park 2D model turned into a 2D CFD model for an area of 2,500 square meter. Now this car park has a varying height. There are some portions which are 2.62 meters, and then there are some portions which are 3.8 meters. And then the number of vehicles around the car park is 94. So for a 3D model, we can see that there are two tube axial exhaust fans, one for normal mode and one for fire mode, and the fresh air has been assumed through the ramp. 15 jet fans have been considered for the movement of air, and they have been placed. So the gray portion is the areas which have the lower height. For the CO simulation, we would even need to calculate the CO flux into the system, which means that we would need to see the hot, this data can be found in ISHRAE handbook, ISHRAE and ISHRAE handbook, where you can calculate the CO flux in a system. The hot engine emission and the cold engine emission, the average of both is taken for 10% active cars. So in this case, for 94 vehicles, we take 10% active vehicles and we calculate the rate of CO production and divide that by the area of car park will give us the mass flux of CO. That becomes the input into the code, your boundary condition for CO. ISHRAE even suggests that for buildings such as stadiums, we can take the operating level to be around 15 to 20%. So now again, going through the process, first we look at the velocity contours. We see that there are quite a few zones which are underventilated and are stagnant, especially in the lower side of the car park. Adjusting the scale to 0.1 meters per second, there are quite a few underventilated and stagnant zones, and especially again in the lower side of the car park. Now looking at the CO contours for the same, what we see is that the CO for 1 hour exposure goes to 130 ppm in that lower side where there was a stagnant zone without jet fans. And with 15 jet fans, that CO remains at 90 ppm. Now, as per ISHRAE, we consider an average of 35 ppm for 1 hour exposure with a peak of 120 ppm. So in terms of ppm, without jet fans, this basement car park is not within the acceptance criteria. And looking at the average CO level, again, we see that without jet fans, there is an increasing trend. So if left for a longer period of time, this CO will keep increasing. It hasn't reached a stable condition, which means that whatever CO is being produced is not being taken out of the system at an equivalent rate. In case of the jet fans, whatever CO is being produced is being extracted from the system and it reaches an average level of 24 ppm. So we can study with CFD what is the optimal number of jet fans, how we should be placing it around the system to get a more stabilized condition and an even extraction of CO from the system. Looking at the third example of a basement car park for fire analysis. Now, again, looking at a 2D CAD model to a 2D CFD model, this basement is about 10,560 square meters. What has been provided is that there is a fresh air shaft marked in green. There are two exhaust shafts. One shaft has two fans of 56,500 CFM, and the other shaft, shaft number 1, has 4 fans of 54,500 CFM. So, and we have 35 jet fans around the basement to optimize airflow. Now, what is expected in this case is that because the fresh air shaft is directly opposite the exhaust shaft, as we had said, the rule for airflow is that it will always choose the shortest path. So we would expect the air to move directly from the fresh air shaft to the exhaust shaft. In terms of boundary conditions, considering this is a fire analysis, we would have to maintain a ACPH of 12 for smoke ventilation. The recommended fire size for 1 car on fire is 4 megawatt. In an area of 2 meter by 5 meter, the fire reaction type is polyurethane for a duration of 20 minutes. The design criteria is that we need to maintain a temperature of less than 60 degrees and visibility of greater than 10 meters at 10 meters upstream of the design fire at 20 minutes. And the visibility should be greater than 10 meters in all escape routes. Now, as expected, when we look at the velocity contours, we see that the air is moving from the fresher shaft directly into the exhaust shaft. It is moving around the left side of the car park into the other exhaust shaft, but the right hand side seems to be underventilated with and without jet fans. So in that case, what happens is if there is a fire in that area, in that left-hand side area, because there is air moving from the fresher shaft to the exhaust shaft of 1,14,000 CFM, 1,13,000 CFM, it kind of forms a wall of air. The wall of air, what it does is it does not allow any smoke to actually move from this side into the exhaust. So the smoke just keeps moving around in this area only, even after 18 minutes, even after half an hour. So the timer goes, the timer is in seconds. And by 30 minutes, it's still concentrated in that area. Now, looking at the visibility and temperature contours, what we see is that the visibility is completely zero for that particular part of the car park at 5 minutes as well as 20 minutes. The temperature is back to normal. So we've taken an ambient temperature of 35 degrees. So by 20 minutes, it's because the fire has now stopped, the fuel has been cut off. We assume a 20-minute fire, the temperature has dropped, but the smoke remains in that area as cold smoke. So that would reduce visibility, and that would cause problems for people evacuating or firefighters trying to access the fire location. Now, there are ways of correcting the problem. There could be that, we could have increased the jet fans, or we could have increased the CFM for the exhaust, but those considering in this particular case, the CFM wasn't the problem. It was that the shortest fresh air path was forming. Those solutions would not have given the correct solution to the problem. So what was considered was a full height wall. What it would do is it would force the air to go around the wall rather than across it. So we are, instead of letting it take the shortest route, we are forcing it to take a longer route around the full height wall. So what it does is, if we look at the visibility contours, the air is forced around the full height wall to now access the exhaust shaft across it. And with the fire in the same location, we can see that now, because the air is being forced around the full height wall, the smoke can evacuate in a much better, faster manner, and we get good visibility in 1200 seconds. Again, looking at visibility and temperature contours, we get full visibility by 20 minutes. And we have our system is back to ambient conditions within 20 minutes. So we can test for car parks or for any other system, we can test whether there is any kind of smoke accumulation, whether our system is extracting the smoke in a timely fashion, whether the visibility is being maintained for a certain period of time before it is impaired, as well as for say a 20-minute duration, that can be studied with computational fluid dynamics. Looking at the fourth example of air conditioning, we have a school auditorium with 4 return air ducts and 4 supply ducts to supply air at 18 degrees. And considering this is for air conditioning, we have to look at the heat load data for that particular system. So we have a room design temperature of 22 degrees, and we have to maintain the temperature of 23 degrees plus minus 1. The heat load is assumed at peak hours, and the heat flux has been calculated for people, roof, ceiling, the walls, the partition, lighting load, and any kind of equipment that has been kept in the auditorium. So there were 2 strategies that were studied for this particular problem. The top image shows the stage side on the left and the auditorium hall in the right side, with supply air ducts coming at the false ceiling and the return riser shown at the side of the hall. In the second image, in the bottom image, ventilation strategy 2, the CFM per duct was increased, and instead of having individual return risers, a boxing was provided for the return risers, with the number of return risers at the back of the hall was increased from 2 to 5. Why that was done was because looking at strategy 1 for the heat load provided, we can see that at 1.5 meter height and 2 meter height, at the back of the hall, because the return risers, there were only 2 return risers, the supply air was not moving towards the back of the hall as much, and there was heat being accumulated. The temperature was rising as high as 27.5 degrees. Whereas in strategy 2, because we have increased the CFM as well as provided more return risers at the back of the hall, the temperature at the back is around 24 degree, peak temperature of 24 degree. We can also see that the average temperature for strategy 1 is 24.6 degree, and the average temperature for strategy 2 is 23.3 degrees. So we were able to decrease the temperature by 1.3 degree. You can optimize this further, or you can optimize this, study the problem in multiple ways to optimize the problem and to understand if you're achieving the temperature and the velocities as expected. The fifth example is for an factory, airflow and comfort. Again, for a factory area, there are multiple equipment which are radiating heat. There are exhaust fans provided on one side with openings provided on the other 3 sides. And then there are some jet fans provided at the center side to propel air from one end to the other. Again, we are looking at 2 strategies. The purple and the green shown within the factory space are the equipment which are radiating heat. The blue is the racks, and then there is a plant room which is shown in gray. The ambient temperature taken as 39 degrees and a west wind of 2 meters per second has been considered. We have to maintain an average temperature of 39 with minimum delta T. So in strategy 1, we can see that the exhaust fans have been mounted at the left end of the factory, with as per the equipment is on the extreme right, and the exhaust fans have been mounted at the extreme left end. And in the second strategy, the exhaust fans have been mounted right above the heating equipment. Again, looking at both the strategies, we can see that the temperature for the first one, where the exhaust fans are mounted at the extreme right, the heat is actually carried from the equipment all through the factory and then exhausted at the right hand side of the factory. Whereas for strategy 2, because we have mounted the exhaust fans right above the equipment which is radiating heat, the heat is contained within that area, and there is minimum delta T, which is of 0.05 degrees centigrade. In strategy 1, there is a delta T of 2 degrees up to human height. Looking at the next case study of a data center, of a data center. Data center, so we have multiple server racks which are radiating heat. There is a return air duct, supply grills, and data tray which is forming an obstruction for the system. And there is hot aisle containment for this particular problem. The boundary conditions to be considered is hot aisle, cold aisle containment, flow rate per pack unit, supply air grill size, temperature, return air grill size, non-operational standby units, number of server racks, heat generated per server rack, air leakage percentage, if any, the hot aisle, return aisle duct material, if to be considered, and if there is any sort of false flow or perforation or grill size to be considered. And then we can see whether there is an optimum airflow happening, because there is a free discharge of air, of supply air into the system. It is contained, hot air contained. So the air discharge is air is being discharged into the system. We can see that there is no stagnant zones or underventilated zones in the data center. And we can also study whether the supply temperature reaching every rack is within optimum limits, whether if you want to maintain it at 21 or 22 degrees, what is the highest inlet temperature which is recorded, what is the highest outlet temperature which is recorded, and whether it is being maintained in a proper manner. For this particular case, we have the supply temperature at 21.5 degrees, and the highest inlet temperature recorded was 22.7 degrees for hot aisle contained data center. We can record the inlet temperature for each server rack and the outlet temperature for each server rack to study whether it is properly maintained. Looking at the section for the same, we can see that the hot aisle containment is somewhere around 30 degrees. Looking at the next case study for a DG set delta T and airflow analysis, we have a DG room with 12 numbers of DG set placed. And the 3D model shows there are in purple, there are 2 ventilation fans dedicated to each DG set mounted right above. There is a sort of a plenum, a wall created behind for getting the supply air inside the chamber, and the exhaust is at the bottom side of that same shaft. So what we wanted to study is whether there would be short cycling of hot air from the exhaust point into the intake side, and then would it be pulled into the DG room through those ventilation fans. Now for the same, for the analysis, the boundary conditions to be considered is the skin temperature of DG set, the heat radiated from engine, heat radiated from alternator, the amount of combustion air, the capacity for each DG mounted radiator fan, the radiator airflow outlet temperature, the skin temperature of insulated exhaust pipes, number of ventilation fans, capacity of each ventilation fan, the lower for intake air with percentage opening, and the ambient conditions like the dry bulb temperature and the wind condition. And what we can see is that in case of such an analysis, whether the air that is being pushed from the DG radiator side, whether it's being pulled back into the intake side. So for the section view, the bottom section view, you can see that some amount of air is flowing back into the fresh air side. And there is some amount of increase of temperature, especially in the center side of the room. So say, for instance, from DG number 5 to DG number 10, there is a rise in temperature around the DG set because this short cycling of hot air is happening. So the delta T in this case is 3.18 degrees centigrade. For a DG room, usually the delta T, considering the ambient condition, it can be from 5 to 7 degrees. So that can then be studied by doing the analysis. And the last case study that I'd like to talk about is an audio analysis, where we have a high-rise building with dedicated audio shafts, where the audio is placed from say floor 0 to floor 50 or 60. And because all the audios, if considered to be working at 100% load, if they are all working in tandem, whether that heat would then affect the audios in the higher floors due to thermal stacking. So because the heat within the system will increase and will flow upwards due to thermal stacking, it may get pulled in by the higher level audio to in the intake side and then derate the audio. So we need to study the same. Now looking at this building, which has 57 floors, 49 typical with 8 refuge floors, and a total of 1776 ODUs in 23 dedicated shafts. 3 capacities have been considered: 1 TR, 1.5 TR, and 2 TR. Again, looking at the boundary conditions, we have the operating ambient temperature, the dimensions of the ODU, the fan air quantity, the fan exhaust temperature, the ambient summer conditions for that particular location, average wind velocity, and the prevailing coincident wind direction. What we can see is that for this particular high rise, if the ODUs are all working in all 1776 ODUs in 23 shafts, we would see in a no wind condition, there would be an updraft of air due to thermal stacking. So even with, if there is no wind blowing, this is for a no wind condition, even without a wind blowing, you would get an updraft of air just because the hot air will rise from floor 0 to floor 57, and it will increase the velocity. So by the time we reach the top of the building, the velocity is 3.5 meters per second. This is purely due to the thermal buoyancy, the thermal stacking being created by the ODUs. And on the right hand side, you can see the temperature for the same. So within the shaft, there is an increase in temperature, and it is rising, and it is affecting the ODUs in the floors which are above it. So for a lower level, you would see that the thermal stacking, because it's starting at the lower level, the thermal stacking is not as much. But as you go to a higher level, you would see that because of thermal stacking, the envelope around the building, the velocity envelope around the building increases. There is more movement of air because the heat is rising. And we can also see that there is some heat which is moving back into the shaft, and it is affecting the inlet side of the ODU. So this is for a refuge flow. We can see that for this particular level, the refuge balcony, for an ambient of 35.9 degrees, the refuge balcony is somewhere around 40 degrees. So there is a 5-degree rise within the balcony itself, just due to the heat being generated by the ODU and the thermal stacking. And by the time we reach to a higher level, we can see that the peak inlet temperature rises due to this thermal stacking. So for a temperature, I'd say for an ambient of 35.9 degree centigrade, we have a peak inlet temperature recorded of 41 degrees. There is a rise of 6 degrees just because of the thermal stacking. So depending on that, we can study whether there would be any derating of ODUs within the system, and whether there is whether this inlet temperature is exceeding the acceptance criteria. So those were all the case studies. Just to summarize, CFD offers an opportunity for validating aspects of ventilation, smoke movement, natural airflow, and thermal comfort right at the design stage in accordance with safety standards and guidelines, and can significantly contribute to an efficient building design. It provides the construction industry with an opportunity to obtain an assurance on effective smoke removal at an early stage when the building design is still on paper. Using high performance computing servers, it is now possible to conduct a virtual hot smoke testing. If any problems are identified during the analysis of results, building design or ventilation strategy can be quickly modified and retested. And time and money required to obtain an optimized ventilation design is marginal compared to what would be incurred on design changes after completion of construction. So basically, it gives you the opportunity to test your design while it's still on paper. You can retest the design if there are any problems which are identified without having to actually physically prototype and without having any structure in place. That's it from me. If there are any questions, I would love to answer them.
Thank you, Shreya. A wonderful session. And I think you can see there are a lot of questions in the chat box. So I think the first one says is, where can I do the course? So if you can help.
Where can you do the course?
For CFD. Yeah.
For CFD, the thing is, there are obviously, universities that offer the course. There are some very good resources that you can find on YouTube itself. If you're interested, you can look up at, just understanding the basics first. To be honest, I'm not very familiar with the courses in India, but I do know that there are quite a good collection of data that you can get on YouTube itself if you were to look, just to start off with.
Yeah, thank you. There is one question. It says how to get details for smoke study like density. So is there any published data, or your book to refer to?
What do you mean by data for smoke? Can you?
So this question is from Majid, and he says that he wants to know the details for smoke study like density and heat generation. So I think the chart that probably you shared here.
Yes. Can you view my screen for fire design?
Yes, it is visible, but I think people would like to, because we are not sharing the PPT as such. So if there is any.
So this one is a very popular one by Kim et al. This was actually.
Can you spell it, please?
Kim, K-I-M et al. I'll just put it in the chat box.
Okay.
It's by AIAA. The study was conducted in the US. They actually had a lot of this is all experimental data where they put certain objects on fire and they studied how that particular material, that particular item behaves and what kind of heat load is produced. So for instance, like I explained, if we look at say wardrobe 1, which is half-inch plywood with clothing on 16 hangers, we can see that the maximum fire load is about 300 kilowatt, 2938, and you would get data for the fire growth and decay as well. So it's a very handy paper to have, and it gives you a very good reference for fire loads.
There is another question by Mr. Vijay Sharma. He says, any certification credentials regarding CFD analysis? I think it is probably a purser to the first question where you can do the course. So correct. If you are doing a CFD analysis, is there any certification of the person doing the simulation required?
So again, I'm not familiar with Indian credentials. So what I have studied is aeronautical engineering with I did a specialization in computational fluid dynamics. So I am a CFD engineer. So that way, I am not sure whether there is anything very pinpointed for it, but I think you need to be a CFD engineer to carry out any sort of analysis. You need to understand the problem statement. You need to understand the physics behind it. to actually carry out the problem.
Yeah, in fact, actually, during the whole of the session, you made it sound so simple, as if it was like a cakewalk. And now when people are asking for it, you say, no, it is not that easy.
It is, see, the thing is, the idea of it, I want it to be accessible to people. It is not easy.
No, I'm just joking. It's on a lighter side.
Right. No, but it has to be accessible. So I don't want to scare people, but it is a steep learning curve. But once you do it, you really enjoy working on it. So please do pursue whoever would like to.
So there is one question by Mr. Saurabh Singhal, and I am not really sure what he means, but he says, for cold storages, how can we calculate fire analysis?
I am not sure.
So, Mr. Singhal, can you put a bit more on your question, because is it pertaining to the the material stored, or are you referring to the temperatures? I don't know what could be your cause, or if you can elaborate more. I don't see. Let's see in Q&A if we have missed anything. Okay, so there is one note from Mr. Mohammed Kirmani Sayed. He says, haven't noticed the northeast, west-south type of winds as boundary condition.
Come again. If we can consider different wind directions, is that what the?
Yeah, I think he wants me to say is that he hasn't noticed northeast, west-south type of winds as boundary.
No, I mean, see, again, it's very location specific. So say I am in Mumbai. If I'm doing any jobs in Mumbai, it's west wind. Now, usually in South India, as we spoke for Bengaluru, it's, if I can just go back to that, it's an east wind of 90 degrees. So it is very location specific. It depends, where you're located, what sort of predominant wind direction is prevailing wind direction is considered for the hottest month. So we can consider any wind direction as per client requirement.
Correct. So I think Mr. Kirmani, it must have been your answer as question is answered. You still you can always reach out to us and we can connect back to the speaker. Closing, I think we'll just probably close at this one. So Mr. Saurabh Singhal has said, again back to his question on cold storages, yes, material stored. So I think you would again refer to the list that you referred,
Yes,
Kim et al,
yes,
which
yes.
probably, so but Kim et al would have, for cold storages, would have stuff like maybe dry fruits, or maybe some people have frozen peas or something. So would they have values for that also?
No, that is that may not be there, but in general, like if you for instance, for a car, if you are taking a 4 megawatt fire, and for instance now, like wood and anything flammable like that, we have a peak fire load of even say 6 megawatt, or I think that's the highest in here, 4 megawatt for a chair 12. So these are generally, for very flammable goods. Now, in case of a cold storage, I'm assuming that these things may not be as flammable, like as fuel producing. Depending on that, maybe, for a higher side, we can take a fire load of say 2 to 3 megawatt. That should be sufficient, but that's again like an assumption.
Yeah, so I think Mr. Singhal, probably if you find some more specific ingredients to talk about, maybe the speaker can find a good reference point to bring back the values that you would want to simulate upon. There is one more question from Mr. Gurudev. He says, can you please explain CFD strategy 2 in Auditorium again? Like in strategy 1, there were vertical return air risers, but what was chosen in strategy 2?
So if you see, what had happened was there are only 2 return air risers at the back of the hall, and there were individual return air risers on the side. In strategy 2, the boxing was provided simply for aesthetics sake, to be very honest. But what was later, the return risers at the back, considering there were only 2 of them, that was increased to 5, and it was equidistantly placed so that we can get a more uniform extraction of heat at the back of the hall. And the CFM from the grills, so these are the supply grills on the false ceiling. The CFM through that was increased to get a bit more cooler air coming down. So if you see the, I think the supply temperatures is at 18, but by the time it reaches the bottom of the hall, it comes to around 20 degrees. So giving that higher CFM just makes it a tiny bit more cooler, and having the number of return risers increased at the back, there is more extraction of heat at the back, which reduces the heat accumulation.
So I hope our question is like, your question is answered. Yeah, he says, okay, thanks. So great. I think, guys, like if you have any more questions, you can always reach out to the secretariat. We will connect to the speaker, try to get an answer to you. If not today, tomorrow, whenever best. You can always also note Shreya's mail ID here, which is right on the screen right now. You can be in contact with her also. Thank you so much, Shreya, for taking out time. Wonderful session. In fact, I kind of started in the beginning and thought probably I'll push out of the show, but it was really amazing. Great. Thank you so much. Thank you, audience, for taking your time out on a busy working day. And I think your applause for the speaker kind of puts of my thank you part easy, because that means both the speaker and the audience have done a good job, and they are really happy for whatever has been done. On behalf of Delhi chapter of ISHRAE, thank you. We will keep on trying to bring more valuable sessions to you, and looking forward to the next sessions that are going to happen. Thank you, everybody. Thank you, Shreya. Thank you, audience. Thank you so much.
Thank you, sir, and thank you, ISHRAE Delhi, for inviting me. Thank you, the participants, for taking time out and being here today. Thank you.
Thank you. Purnima or Shyam Singh, can you close the session now?
Yes, sir.
Yes,
Thank you, sir.
Thank you.
Thank you, ma'am. Thank you so much.
Thank you, madam.
Thank you.